All right, what's done with that? I need to open up my calc. Today, we're actually moving into one of our last statistics that we're going to learn. It is, oh my goodness, that wasn't even close. Our last statistic, it is called a chi-square statistic. It will be abbreviated something like this. You've seen it in your calc already. It looks like x squared. That's kind of, you're getting warmer. You're still missing by a lot. Chi-squared is the statistic's name. It looks like an x. That's the Greek letter x for chi squared. That's what it's abbreviated. Now, if you would, I ask you to grab your formula sheets. Look at your formula sheet. The very last page on your formula sheet should look something like, it is not a normal distribution. That's the first thing you should notice when you see that chi-square statistic. It is skewed to the right. This is always going to be a one-tailed test. I'm almost there. There we go. Skewed right, always a one-tailed test. Our hypothesis test will still be null alternative. It'll still be, this will be an alpha or a reject region. We'll be looking for a p-value. We continue to compare p-values to alpha values. We also have degrees of freedom, just like our t-distribution. So we will have degrees of freedom, and we will do the rest of it exactly as we've done our other 8. Now, TI, what is it, 83s? TI-83s don't have both statistics. As I told you, we're going to look at 3 applications of chi-square. There's 3 of them. Your calculator, if you have a TI-83, will only do 2 of the 3. Okay? So you're going to need to know how this formula sheet or the spreadsheet works, and I will cover it again so that you can use it. So I'll explain that as we get to that point. All right. Mr. Wood, what does a chi-square statistic do? Why are we talking about this? What's the significance? Well, the major piece of information in this problem and what the statistic does is we are now going to re-talk about categorical data. Everything we've done up to this point really in regards to inference has been about numerical data. Remember the 2 branches of categories of data, categorical and numerical. We had proportions and we had means. We could average it. We could count how many people out of how many people decided they wanted to vote for the president. Proportions, numerical. Means, numerical. Today, categorical. Categorical data, it doesn't make sense to average it. Okay? Categorical data, something like, I can do proportions out of categorical data, and I'll talk about that in a second. But the biggest thing that I want to look at is realize that it doesn't make sense to average categorical data. For example, if I conducted some sort of poll here, and I wanted to figure out everybody's favorite color. In fact, let's do that right now, just to show you. Okay, I'm going to look at the colors of the rainbow. What are they? Roy, red, orange, yellow, green, blue, indigo, violet. Okay? You can only vote once. You got to pick one of those colors. Everybody votes once. Okay? We're just going to generate some quick categorical data. Okay? If your favorite color is red, stand up, please. 3. If your favorite color is orange, stand up, please. 1. If your favorite color is yellow, stand up, please.
I'm getting there.
1 yellow?
Yeah.
Favorite color is green, stand up, please. 1, 2, 3. Favorite color is blue, stand up, please. Good Lord, it's a lot of blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Indigo, what color is that? What color is indigo? Blue, purple.
Can I vote twice?
You cannot vote twice. 1, 2, 3, 4. And violet. 2, 4. All right. Do we agree that this is obviously categorical data? Okay. It makes no sense for me to average these numbers together. If I put 3, 1, 1, 3, 13, 4, and 4 in list 1 and found the average of it, what would I have the average of?
People voted to.
What would the number represent? Absolutely nothing? Do you agree with that? Okay, yeah, people who chose a color. All right, so, yeah, on average, the average amount of votes per color? Well, that could be, I guess. Yeah?
You go, you guys.
Now, realize, and this is the gray area, I think it makes sense to you guys that we're not going to average those numbers and do any statistics with any real meaning to it. In a chi-square test, I will look at all the data pieces. Okay, I'll say that again. When we're doing the chi-square test, I'm looking at all the categorical data pieces here. Owl, that's an owl and an owl, I don't know. We're looking at all the categorical data pieces. Now, I could present to you guys this exact same data set. Think about where you were on the last exam. The exact same data set or yesterday's quiz. Is there a difference in the proportion of students who like the color blue and like this color violet? Well, yes, we can look at it visually. Could you do a two-proportion z-test with the proportion of blue versus violet here?
Sure.
Do you see how it's possible to do that two-proportion z-test? Realize when I'm doing the two-proportion z-test, I can only pick two of these categories and compare them. And it does need to be proportions. Notice that I'm not using all the data pieces in that case. So it is possible with categorical data like this to do a two-proportion z-test. But realize I can only pick two categories when I do it. Do you guys kind of see the big difference between a chi-square and a two proportions? Does everybody agree with what I'm talking about? Okay. Chi-square uses all it. So we'll come back to that. And we'll kind of look at the chi-square goodness of fit. What I love about this statement of the test, all you're comparing it to is how good does my data match what's supposed to be true? In other words, how good does my data fit with what's supposed to be true? Does that make sense? So goodness of fit in this case, just like many of our other stats tests, it's telling you what it is you're looking for in the context of the problem. How good does your data fit? Does it fit with what I hypothesize to be true or not? So we will abbreviate. Your book uses the pies for capital letter P. Again, AP exam and me, I will use capital letter P for that. So P1, P2. Again, we're looking at proportions. Proportions and actual data pieces. I'll explain that proportion piece in a second. Your book uses pi. I use capital letter P. We can have multiple categories. In the example that I just showed you, I think we had 6 categories. Is that right? Okay. So this would go P1, P2. And in the context of the problem that I'm just now talking about, we would say P1 equals the true proportion of students who prefer the color red. P2 would be the true proportion of students who prefer the color orange. P3, do we see where I'm going with this all the way down? Do I need to do that whole thing? In fact, on the AP exam, for a problem like this, you're welcome to establish the pattern and then put dot, 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 and then in the pattern. Okay? And that's even going to be the way that you show your work as we do this crunch. Okay? Establish the pattern. P1 equals the true proportion of students who prefer red. P2, true proportion of students who prefer orange. Dot, dot, dot. P6 equals the true proportion who prefer violet. P7, sorry. Okay. This should make sense to you right now. You do not have to include this, but that thought should make sense to you. In other words, the proportion of red plus the proportion of orange plus the proportion of yellow plus the proportion of green, blue, indigo, and violet should sum up to 1. Okay? All right. Null and alternative hypothesis. Super simple in this one. Actually, your alternative hypothesis is super simple. Okay? Null hypothesis. And I will use big P's. P1 equals whatever you say it's supposed to be. P2 equals whatever you say it's supposed to be. Everything equals whatever you say it's supposed to be. Because the statistic is goodness of fit. Does your data that you have fit what's supposed to be true? Yes or no? That's really all this says. Yes or no? Your alternative hypothesis can be a sentence. I usually just write this. At least one of the true category portions differs. And I usually just say my alternative, at least one proportion is incorrect. Because if one's wrong, doesn't that mean at least two are wrong? Because they all have to sum to 1, right? Yeah. Well, if I said one's supposed to be 20%, but in reality it's 15%, doesn't that mean not only the 20% is wrong, at least one of the other categories is wrong? Does that make sense? So that's what the alternative is. Either our data matches what it's supposed to match, or something's wrong. At least one of them's wrong. So that's all you need to say. It's also fine to write the null hypothesis is not true. That's also okay. I'd prefer to see at least one proportion is wrong because it helps you write your conclusion better. Okay? All right. Here's what the chi-statistic is. Here's how you calculate it. You guys still need to get that down? Sorry. There you go.
So when you're writing the null hypothesis and you're saying that each P, like each color.
In this case, it would have been P1 equals hypothesized proportion for red. P2 would have been hypothesis, P little subscript 2.
And then you would say that that's all true. And then for the
Alternative,
one just has to be wrong.
all I have to say is at least one's wrong.
At least one over
Yeah.
out of like how many?
Well, in this case, there's 7 categories. Remember, they all have to sum. That's what I said. They all have to sum to 1, right? So let's say that this one I hypothesized to be 20%. But my data says it's not 20%. My data says it's like 15%. Well, my data says that one's 15%. One of my other ones over here is going to have to compensate for that difference. Because this one's at 20. So that difference was 5%. That means at least one of my other ones over here must be off by 5%. Or this is off by 5%. This one's off by 2. This one's off by 2. And this one's off by 1. At least one of them's off by another percent. That's what my alternative is. All right. Okay to go? Here's what you need to do to calculate the chi-square. It's observed minus expected squared divided by expected. I'll show you how that works. And you're going to sum those up. Just remember observed minus expected squared divided by expected. It's a different statistic than your other statistics. Notice that all of our other statistics kind of flowed in one direction, like x bar minus mu divided by the standard deviation. X bar 1 minus x bar 2 minus, right? A lot of our other statistics, very similar. This is different. Why is this one different? Well, we're dealing with categorical data. All the rest of our data was really numerical. Again, observed minus expected squared divided by expected. And the chi-square is actually the sum of all of those. We'll sum them all up. And I'll show you. We're going to get to an example in just a sec here. For those of you guys who do have your formula sheets out, I don't know if they give you this formula or not. I think they do. It's on page 2. Is that right? So if you guys look on page 2 of your formula sheets, you'll see it. It's at the bottom. Is that right? Okay. Look at the bottom, and you should see something that looks like that. Again, that formula is given to you. I already kind of told you that. So, two big assumptions. Again, think about step 5. Step 5 on your tests. Tell me what you're doing and why you're doing it. Usually it's random, independent, and normal. Agreed? Random, independent, and normal? Isn't those the 3? I've hammered them over and over and over again. You guys are tired of writing them? Okay? Now, in this case, we still need random. We still need it to be sufficiently large. Obviously, if you put that away, if you look at this distribution, you're not justifying normality, are you? Since this distribution is skewed right, the chi-square distribution is not a normal distribution. It's not bell-shaped, it's not any of those things. So, random, independent, and normal, we don't want to test for normality here. We want random, we want sufficiently large. Sufficiently large is every cell count is, expected cell count is at least 5. Again, I'll say it, expected cell count, not actual spell count. Spell count? Cell count. I don't know where spell came from. Expected cell count. We'll talk about expected in a sec. The third thing that you need, instead of random, independent, and normal, we want random, large enough, and categorical. Identify it as categorical data. That's your big flow point. If you have categorical data, there's really only 2 sets of tests you can do. You can do the chi-square or you can do proportions. Those are the only things you can do. For our numericals, we're going T's, we're averaging, and it makes sense to do that. Okay? This is your step 5 justification for the chi-square. Data. Here we go. This applies for our class. Again, we're complaining about the dice. They seem to be loaded. The dice were taken off the table. It seems like you get 5 all the time in this class. The dice were taken off the table and tested one at a time. One die was rolled 300 times, and the following frequencies were recorded. So anyway, I took a dice. Some gamblers said, you know what? I think you're cheating. The dice is loaded. And loaded dice is what happens. I don't know if you guys have any experience with it or not. What they do is they will, dice that they use at casinos are all, it's a perfect cube. This dice actually is rounded a little bit. I don't know if you guys can see. But it is rounded. Dice at casinos are perfect cubes. Equally weighted, so each side has an equal probability of rolling face up, face down. That should make sense to you. We call that a fair die. What you do if you have a loaded dice, you can shave off edges so that it will roll off an edge and land on one of the faces more frequently. One way to get loaded dice is to shave edges. Another way to load your dice, and that's where the word loaded comes from, is to weight certain faces by drilling in, putting weight in, and sealing it back up, so that when you roll it, the heavier side will face down more frequently and the light side will face up. So you shave your edges and you have weighted dice. Those dice now will occur with the probability or the outcome that you want to bet on. Does that make sense? Good loaded dice are very hard to define or see visually. You can't look at them. They have to be tested. And this happens in casinos frequently. Because what happens in casinos, have you guys seen the big craps game? I'm sure you guys have seen movies and stuff where they're shooting the craps at the table, right? What happens is sometimes the dice will be shot off the table. People who have loaded dice will have their loaded dice in one hand. They will pick up the dice that went off the table. They'll switch them for their loaded dice and put the loaded dice back on the table. But if you think things through statistically speaking, if I can predict what numbers are going to come up on the dice more frequently than not, Because do we agree that the most common roll on two-sided dice is 7? But if I've loaded the dice so that's not 7, but instead say 9, can I bet that? And over time, will I make a lot of money if I know that 9s are going to come up more frequently than 7s? Because statistically speaking, 7s will come up much more frequently than 9s. That make sense? So that's how the game works. Real deal here, so we got 300 dice, and they test it. They'll pull dice off the table. In fact, if they think you were the person that put the loaded dice on the table, they will take you and put you in a special room while they test the dice, and then they'll go back to the cameras to see if you actually swap the dice. You know those Ocean's 11 movies and stuff like that? Stuff is a real big deal. Obviously, it's very dramatic in the movies. It is a big deal in casinos. Casinos don't get beat. Casinos are the best mathematicians out there. They're the best statisticians out there. Because they know over time they've got probability on their side. Does that make sense? Should at the end of this class. So they're going to take this dice, they're going to roll it 300 times. When they roll this dice 300 times, they got 62 1s, 45 2s, 63 3s, 32 4s, 47 5s, and 51 6s. First thing on this problem is I need you to realize that this is categorical data. Students say, Mr. Wood, no, it's all numbers. Has it happened on AP exams? Yeah. Oh, crap. They'll come to me the next day after the AP exam. I did a, well, I don't know, a difference of means or something like that. They averaged them together. I saw all numbers. Yes, you're right. They're all numbers here. But realize we're talking about how many times you rolled the number 1, how many times you rolled the number 2. This is a category up here. The outcome is a new number, but it's a category. Does that make sense? Okay? So, really what we're looking at with this distribution, is this evidence to say that that die is loaded or not? Do you guys see the next question? Okay? So, we're going to test it at the 1% level of significance. This statement that I gave you should make sense. If the die is balanced, all outcomes should have the same expected frequency. In other words, if the dice is fair, then it should land the same side with equal probability. Does that make sense? Okay. So, how many times should each side face if the dice were fair? Go, people say 50. 50 is correct. How did we get 50 there? 300 divided by 6?
Oh,
300 divided by 6, how many people? Equal probability. I want an equal chance on each of them. So it'd be 300 divided by 6, which in this case, and I'll come back to it and formalize it in a second. I'm just kind of thinking out loud. Do we agree that if every one of those rolls were 50, then I would definitely reach the conclusion that that dice is totally fair. And we also agree that law of large numbers thing says in the short run, say 300 rolls of the dice, I'm not going to get perfect 50, 50, 50, 50, 50. But over time, it will average out to that. You guys see that connection for law of large numbers there, right? So now, do we notice that there's discrepancies with each one of these categories? My question is this gap big enough to say that the dice is loaded, or is this gap not big enough to say that the dice is fair? And think about it in terms of null and alternative hypothesis. Evidence. Is there enough evidence here to say that the dice is loaded, or even though these numbers don't match up completely, do I come back with I do not have enough evidence to say that the dice are loaded? Does that make sense? Could the dice still be loaded with this? Yeah. Okay? So that's kind of big connections here. Let's go ahead and get into the 8 steps now. First step, step 1, define what it is you're talking about. So we're going to let P1 equal the true proportion of 1s rolled P2 will equal the true proportion of 2's rolled. And as I said, once you establish your pattern, you can dot, dot, dot that in the pattern. In this case, it'll end at P6, and that will be the true proportion of 6's roll. For me, and the AP exam, establish that you know what you're talking about, but you're not going to waste your time listing it all out because it's a waste of your time. And time is an issue. Does that make sense? Okay, so that's step 1. Step 2, and your null and alternative hypothesis will sometimes change. In this case, and I'm going to do another example in a second. In this case, our question that we're talking about is, does this data indicate that the dice is unbalanced? Okay, so what we're going to assume to be true in this case is that the dice is fair. Does that make sense? And if the dice is fair, that means the proportion of 1s will equal the proportion of 2s, will equal the proportion of 3s, will equal the proportion of 4s, which equals the proportion of 5s, which equals the proportions of 6s. What should all equal what proportion?
Oh, wait. Point. Point 16. I was like, what's...
Don't hurt yourself thinking.
I couldn't think of like what 1 divided by 6 was. I was like, point.
1 over 6 works. Okay? Remember, yeah, I said they all sum to what value? They all sum to 1. In this case, I'm assuming the dice is fair. If the dice is fair, the number of times, the probability that I roll a 1 is the same as the probability I roll a 2, same as the probability of 3, as a 4, as a 5, or a 6. What should be 1 out of 6 times? That null hypothesis will change for other values, for other problems. So context is a big one on these. Alternative hypothesis is really easy. You can just say the null hypothesis is false, which is to say at least one proportion is incorrect. And in this case, if at least one proportion is incorrect, that's evidence to say that we have loaded dice and there's cheating going on. Null alternative. Let's see. What level did they tell us the test looks one at? 1%. That's a free point on every test, basically. Alpha 0.01. And we are now using chi-square. And you do need to identify this by name. Yes, question?
For the alternate hypothesis, is it possible for us to just say what proportion does not equal 1/6 in this case?
Say at least. The words at least here are big because it implies that when you say at least, you are understanding that if one proportion is off, that's more than one are going to be off. Because I can't just have one proportion be off.
Okay.
You know, I can't. I have to have at least one, more than one off. Identify it by name, please, chi-squared, because tomorrow we're going to learn the 2 other chi-square tests. So today we're looking at goodness of fit. Okay, chi-square goodness of fit. And what assumptions are we going to make, or why am I justifying using this? First off, this is categorical data. Next up, each expected cell count is greater than or equal to 5. In this case, I would just say equals cell count, expected cell count is equal to 30. And I got that, 50, isn't it? Sorry. And that was 300 divided by 6. Let's see, categorical and rolling of die is random. Random, categorical, large enough. Moving on to step 6. Agree with that? Okay. Step 6, write it dry and then show me the setup. So chi-square equals the sum of, I just write observed minus expected squared divided by expected. And that sums on the outside. Okay? There's the dry. Here's how the statistic is calculated. I'm going to grab it. You guys have the data listed. For the number 1, there were 62 actual data pieces, so I'm going to say 62 minus 50 divided by 50 squared. That's for the first data piece. My next data piece is 45 minus 50 squared over 50 plus. You guys see the pattern for this? So all you have to do for showing your work, establish your pattern with what you're doing, dot, dot, dot. Show whoever's looking at your work the last one too. So do the first, the second, show that you're continuing the pattern. You are summing all of these up. And the last one in the pattern will be 51 minus 50 squared. Okay. Now this one's small enough. There's only 6 data pieces. You can actually do this statistic by yourself if you'd like. I'll show you a couple different ways. Let's see. Let's go to put your data into list 1. Data in list 1. What do we got? 62, 45, 63, 32. If you wanted to do this kind of by hand, then you'd go and put in list 2, 50, 50, 50, 50, 50, 50. So is it observed minus expected squared divided by expected? Agreed? So I could go make list 3. I could make list 3 equal to, where is it? List 1 minus list 2 squared divided by list 2. Do we agree? That's kind of what I told whoever was grading my paper. That's what I was doing. And to get the statistic, all we have to do is sum that up. That's closing it out, it's finishing it up. So we'll sum list 3. And that's under there, list 3. So our chi-square statistic should be 13.44 here. Does everybody see how the formula, you're just using my calculator to shortcut that. This is how you would do it if you have a TI-83. It's not that hard to do it just by hand if you don't have one. What did I say, 13.44? Everybody okay with that? Any clarifications on that? Okay. Go to stat. Go to tests. Some of you guys will have this button, some of you will not. We are doing a chi-square goodness of fit. If you have the chi-square goodness of fit, you can do it for today's material. If you don't have the chi-square goodness of fit, you have to do it by hand like I just showed you. Chi-square goodness of fit, you'll hit that. Your observed values are in list 1. You have to put your expected values in list 2. Okay? So you still have to put list 1, list 2. That's why I said this button's not that helpful. I don't know why it's not on the old calculators, because going into list 3 and calculating it for you like I just did is all what this is going to do for you. Does that make sense? So there's not much. It's almost the same. Degrees of freedom will be categories minus 1 or k minus 1. So we had 6 categories. We have 5 degrees of freedom. You will need to input that and then hit calculate. And I'm sure we're going to be shocked to see that it's 13.44. I can't talk today. I don't know why. So what's also nice is if you're looking at this, this is actually giving you what was in list 3 that we created in list 3. You see that if you look at list 3, the first value is 2.8. So again, 13.44, degrees of freedom is 5, and we have a p-value of 0.02. For those of you guys who are, how many people do have the TI-83s? Okay, so you guys don't have that goodness of fit, that's correct? I think TI-83s are the only ones that don't have that goodness of fit.
That's the only one.
Yeah, that's the only one out of the 3 that you don't have. Go to your formula sheet and look under 5 degrees of freedom. I'll pull it up right here. Formula sheet. This is actually good general information for all of you guys. You're going to look under the row of 5 degrees of freedom for chi-square. 5 degrees of freedom for chi-square. You're going to go till you get to where, what were we, 11 point, what?
We were 13.44.
13.44. So if you look, 13.44 is between 13.39 and 15.09 at 5 degrees of freedom. Again, at 5 degrees of freedom, you look to find your chi-square value. Your chi-square was between 13.39 and 15.09. Go up to the top. That will tell you the probability. It's between 0.02 and 0.01. So your p-value is between 0.02 and 0.01. We know that it's greater than 0.01. Does that make sense? And that's what we got as output for our calculator also. Our calculator output said we would round that to 0.02. Okay? So 13.44 with, I'll say, k minus 1 degrees of freedom. That is categories minus 1, so 6 minus 1 degrees of freedom, which is 5 degrees of freedom. The p-value is approximately 0.02. K is the number of categories.
Oh,
Yeah, it's degrees of freedom, but there are 6 categories. So now we're kind of at the end. We'll close it out. Step 7. Our p-value is less than, no, it's greater than. It's greater than alpha. 0.02 is greater than 0.01. So that's going to be a fail to reject the null hypothesis. And we will say at the 99% confidence level, there is not sufficient evidence to say at least one of the proportions is incorrect. Okay. Again, really a lot more of the same, but kind of looking at things in a new way. Really, the new thing is categorical data and how the statistics is calculated. Tonight, you guys will have chi-square to work on. It's just going to be goodness of fit. We will move into the other 2 tests tomorrow. We will correct quizzes tomorrow because the bell's going to go. What time we get out? Yeah, pretty quick. So the bell's going to go. We have slated a quiz tomorrow. The quiz will be on Friday, not tomorrow. Okay? So quiz Friday, not tomorrow. Test we'll be reviewing on Monday. Test on Tuesday. So quiz Friday. We'll recorrect quizzes, or we'll correct quizzes tomorrow in class.